Alright, so today I am going to teach you a new topic. It is called recursion. It is a fun one. There's a lot of memes about it on the internet because it's a very hard topic, and so people like to make fun of it. Why not? So recursion is, depending on how you feel about things, potentially the most difficult concept in this class. Either that or pointers. Take your pick. Recursion is going to be so fun, though. I love it. I love teaching it. The idea of recursion exists in all these pictures. Like, have you seen this fractal before? You know what fractals are? It's like, here is the whole thing. Here's the Sierpinski triangle or something. Do you see how it exists within itself? And then you got it within itself again. You got it within itself again a million times. You just keep zooming. It's always there, the same thing. That's recursion. These Russian stacking dolls. You got a doll, but if you open that up, you find another similar looking doll. And it just keeps on going smaller and smaller and smaller and smaller. But you do have a smallest doll. That's probably the best example of recursion. That's recursion. You find the same thing inside of itself. And so my last silly example is this was like an old, I can't remember if it's coffee or tea. So the tin for either coffee or tea. And that's in French. And on the tin is a woman holding a cup of either tea or coffee made with this thing, which also has the tin on it. And then there she is again holding the tin with herself on it forever and ever and ever. So that's the idea of recursion, okay? We're going to learn how to make that kind of stuff appear in a program, things inside of themselves, okay? So that's where we're going. Do pay a little bit of extra attention because it is a traditionally hard topic for CSCI 40 students, okay? But again, the memes, there's so many of them because everybody doesn't like recursion. They want to commiserate. Alright, so let me first talk about the opposite of recursion. That's called iteration, alright? Up until now, recursion solves problems like a loop does almost. Recursion solves repetitive things, like you can find the same thing inside of itself. You're doing the same thing a bunch of times. So the other way you can do the same thing a bunch of times is to use a loop, right? Up until now, you've been using what's called iteration to solve your repetitive problems. And so if I say the word iteration or a solution that's iterative, that's the adjective, that just means you're using a loop, like a while loop or a for loop. Recursion is loops without loops. Right? And obviously that makes zero sense to you right now. We're getting there. So this is iteration. For int I equals 0. Everything you know so far that repeats stuff, that is called iteration. I is less than 42. We say that the variable I is iterating over the numbers between 1 and 41. You heard me say that word before, right? Then you give your body. That's called iteration. Recursion is a competitor. You can do the same stuff with recursion. Just looks a bit more weird, all right? So here's closer to a problem that we can code up, all right? So here's like the basic idea of recursion using factorial as the example. So first of all, I guess let's define it. So recursion is when you are solving a problem in terms of smaller versions of that same problem, okay? You're like handing off the problem to itself, but a smaller version, all right? Smaller versions of the same problem, and you end up building up the original answer that you're asking for, the answer to the original question, using those smaller solutions, okay? That's going to be the goal. That's what recursion does for you. And so I claim that factorial, finding the factorial of a number, is a recursive problem, all right? So do we all remember what factorial is? It's the exclamation point in math. 5 factorial is 5 times 4 times 3 times 2 times 1, that thing. That's factorial. That's a recursive problem, I claim. All right. So here's a question for you to ponder. Let's copy this again. Factorial is a recursive problem, which means it exists. You can find factorials inside of factorials. Do you see, discuss with your neighbor, do you see a smaller factorial inside of 5 factorial? Potentially multiple smaller factorials. Take a minute to discuss with the people sitting next to you. Do you see a smaller factorial here inside of 5 factorial? So like we're going to define 5 factorial in terms of another factorial and maybe some extra work. Alright, do we see one? Somebody tell me, where's a smaller factorial? Yeah.
Factorial of 5 is just factorial of 4 times 5.
There it is.
Factorial of 4 is just factorial of 3 times 4.
You're getting it. So there's 4 factorial. That's the next smaller factorial. Do we see how 4 factorial is baked into 5 factorial? It's secretly there. And then inside of that is 3 factorial. You can circle that too. There's another factorial, 3 factorial. Then there's 2 factorial. Then also there's 1 factorial. Technically there too. They're all there. But usually with recursion, you want to find the next smaller one. So 4 factorial is the one that you should see. That's the one that should pop out at you. Right? And so we can define then 5 factorial in this way. We can say 5 factorial equals 5 times a smaller factorial. Interesting. Okay? Does that make sense? Just logical, right? That's going to lead to a very powerful thing for us. All right? So let's talk about how we are going to make a recursive solution. So 5 factorial, we've noticed, that's equal to 5 times 4 factorial. And then we can break that down further, can't we? 5 factorial, we notice that's equal to 5 times 4 factorial. But what is 4 factorial? But 4 times 3 times 2 times 1, which is 3 factorial secretly in there. You see that? So 4 factorial is 4 times 3 factorial. 3 factorial is equal to 3 times 2 factorial. So in general, what have we just noticed? In general, you ask me for any factorial, so that's an exclamation point. Any n factorial is equal to that original n, right? N factorial is equal to the original n, like 5 factorial is equal to the 5, times n minus 1 factorial. That is your general solution. Does that make sense? This is called the recursive case of the factorial problem. The recursive case. Because it's using a smaller factorial. You found the problem inside of itself, right? The recursive case is when you use the smaller subproblem. This is a subproblem, it's a smaller one, to solve the original bigger problem by doing some extra stuff. Multiply by your n. That'll do it, right? But you don't want this to go on forever until the end of time. You want to get to an answer eventually. So the recursive case, you have to pair it up with at least one stopping condition. All right? And then for that, to find that, you ask the question, like, when does the factorial problem get so small that, like, I don't need to go out and hand it off to a smaller factorial? Like, it's small enough I can immediately solve it. All right? Or if I keep following the recursive rule, when does it stop making sense? That's another question that is valid to ask. So, all right, let's keep going. 3 factorial does equal 3 times 2 factorial. That is correct. That works still. All right? Let's keep following our recursive case rule until it gets small enough where it starts breaking down. All right? So 2 factorial, that's equal to 2 times 1 factorial. That makes sense because 1 factorial is defined to be 1. So this could be a good stopping condition maybe, but let's keep following it. 1 factorial, if I were to follow this recursive case rule, that's equal to 1 times 0 factorial, right? Just plugging in the numbers. And technically this is okay. 0 factorial in math is defined to be 1. That's okay. So we can keep going. All right, 0 factorial, what's that equal to? That's equal to 0 times negative 1 factorial. And this is definitely a problem, right? Because this makes the whole answer 0 for everybody. We don't want to go that far. So we should not have come to here. And also the factorial of negative numbers does not exist. It's not defined. So that is, we should not have gone that far. All right? So we could have stopped at 0. We could have been like, all right, if you see 0 factorial, that's just 1. The answer is 1. That's in the math book. We're done. Don't go any smaller, because we'd run into problems if we did. So we could stop there, but we could also, just to make it easier on ourselves, like 1 factorial. It's just 1, right? That's the answer. We don't need to go that any farther down. Let's stop there. All right? So let's notice that. This is a nice stopping point, all right? Boop. 1 factorial. A nice stopping point, we noticed. Because if you just see the number 1 and you're asked for the factorial of it, you just be like, oh yeah, the answer is 1. I'm done. Okay? And so let's define that. That'll be our second rule. Right? If you get down to 1 factorial, somebody's asking you for that, just immediately give back 1. You don't need to do any smaller factorials. Right? And so that stopping condition is called a base case. Every recursive rule, every recursive case needs a base case somewhere to stop it. Otherwise, it would just keep going forever, right? Infinitely. We don't like that. So that is your base case. And so with those 2 rules, this generic rule for every number but 1, and this rule, this base case rule for the number 1, then we can solve any factorial of any number greater than or equal to 1. Okay? Are there any questions about that? We just noticed that. This is a generic rule, a general rule, a recursive rule for the factorial defined in terms of itself. And you can keep on plugging that rule for smaller and smaller values until you get down to 1, and then you can build up the final answer. Okay? So in pictures, we have a base case and a recursive case. Base case is you ask me for 1 factorial, the answer is 1. Recursive case is you ask me for n factorial for some other number that's not 1. That's equal to n times n minus 1 factorial. We noticed that. All right? So let me show you how both of these will compute a valid factorial. So like if you ask for 5 factorial, that's not 1 factorial, so we're going to run the recursive case rule. That's equal to 5 times 4 factorial. And again, we can run the recursive case rule on 4 factorial. That's equal to 4 times 3 factorial. You see that? 3 factorial is equal to 3 times 2 factorial, running our recursive case rule. 2 times 1 factorial. And then finally, we hand off this problem to the base case. You ask me for the factorial of 1. Oh, the answer is immediately 1. And so that's your first answer, and then you just start giving that back. All right, like, okay, my answer is 1. Give that back to whoever asked for 1 factorial. Okay, yeah. And then 2 was waiting to multiply its 2 by that, and then now it has its answer for 2 factorial. It can give back 2 to whoever was asking for 2 factorial, which was 3 factorial. And it saw 2 as the answer for 2 factorial. It was waiting to multiply its 3. So now it knows that the answer for 3 factorial is 6. It can hand that back up the chain. See how that's working? That's how you can use the recursive case rule and the base case to solve a factorial. And so this got 3 factorial's answer for 6. And then we can multiply that by 4, get 24. That's the final answer for 4 factorial. Give that back to whoever was asking for it. It was 5 factorial, waiting to multiply its 5 by that 4 factorial, which is apparently 120. All right? And so that's how you work your way down to the base case and then start building the answer back up. That is recursion in a nutshell. Are there any questions about that? This rule would not work for negative numbers. Like, if you gave it this, it would just keep on going forever. Negative 2 factorial, negative 3 factorial, negative 4 factorial. We don't like that. Same with 0 factorial. It would never solve that. So you have to watch out for those. But any normal number is going to get the right answer. Okay? So, can we formulate any questions that we have about this? Or is it just too weird? Are we ready to code this up? Do you want to see what this looks like in code? Because there aren't going to be any loops. Recursion is going to do the looping for us. So, okay. When we write code, we usually are solving problems by writing a function to do that, to give us back the solution, right? So we're going to write a factorial function. That's going to be the start of it. It's going to be called fact or something. It'll take the n that we want to calculate the factorial of. It'll return an int because factorials give back integers, right? And then we have a body. And the trick is going to be, all right, we're writing a recursive solution, we're going to be asking for, in factorial of n, we're going to be asking for the factorial of n minus 1. What does that mean in terms of a factorial function? Well, who gives me the answer back for factorial? It's me. I give back the answer for a smaller factorial. So a recursive function is necessarily a function that calls itself on a smaller input. Okay? So we're going to be calling fact of n minus 1 inside of the implementation for fact in the recursive case. And that should disgust you. That's brand new. That's a little weird. It's really weird. But that's going to give us the answer. As long as it works its way towards the base case, as long as it gets smaller and smaller, eventually it'll hit the base case and start building the answer up. All right? So inside of the fact function, we got those two cases. It's going to be the recursive case, which is n times n minus 1 factorial. What does that mean? You give back your n times just the factorial of n minus 1. That's what the answer looks like. You call yourself. And then the base case is if n was 1, just return 1. That's your final answer. Okay? That's it. That's surprisingly it. There are no loops. It's just the way that functions call and return will do the looping for us. All right? So let's code that up. All right? Let's code that up. Let me show it to you. It will look weird the first time you see it. So I'll ask for factorial of 5. And we shall see 120 printed once we do this. So int fact int n. And so the job of this function is to return n factorial. And so our goal is to figure out like which case are we in first, because we don't know like which do we return, which case are we in. So we got to figure out, are we in the base case or the recursive case right now? So we're in the base case if n is 1. We ask for 1 factorial in that case. Base case 1 factorial is just 1, return 1. Otherwise, else, we were. So we're in the recursive case. And we know that the recursive case rule is n factorial is equal to n times n minus 1 factorial. All right? So, translating that, our answer is our n times the factorial of n minus 1. That's a smaller problem, and it's our job to give back factorials, so we're calling ourselves on a smaller input. That's it. No while, no for anywhere in sight. But I get my answer. I get 120 back. Woohoo. Any questions about how the code is the equivalent of the rules that we created? Because it just seems like magic, right? I love recursion. So you could also have used loops to do the exact same thing. So I want to show you that because maybe that's easier in your mind right now. So let me show you how to do it iteratively. This was the recursive way. Let's do it iteratively too. Int fact iterative. Int n. And so what is the factorial? It's just a big product, right? So you ask for the factorial of n, int product, start it at 1, and give that back. So it's like, I don't know, you're just multiplying all the numbers from n all the way to 1 into product. Int I equals n, I is less than or equal to 1, I minus minus. It's like 5 times 4 times 3 times 2 times 1. You work your way down. Product times equals I. That would also work. And maybe that makes more sense to you right now. It should, because you're used to loops. So you get the same answer. But this is doing that. It's doing a loop somehow, and it's giving you that same correct answer back. So how cool. We're somehow doing this in a weird way inside of this function. Cool. All right. Any questions before I draw a picture of how this is working? Yes?
If you were to do n, just fact n or fact n plus 1 in the function itself, would that just continue on forever?
Yeah, because it would never make its way to the stopping case. Yeah, I think the picture I'm about to draw will show you why it would keep going.
What if you did n minus or n plus 1, but you did the stopping case as like 6 or 7?
That would be okay, but like that doesn't make sense for a factorial. maybe some
I
other
understand
solution.
that, but that would still like.
Yeah, as long as you eventually get to 6 or whatever your base case is, then it's good.
Makes sense.
Yeah, it depends on the problem, I guess is the right answer. So we now have options. So we can make the recursive way, we can make the iterative way. There's always two options. You can always make something with loops into a recursive answer. They are equivalent in power. You do not need while or for, you just need recursion, or vice versa. Sometimes, though, it is much easier to think about a recursive answer. Maybe not for factorial, once you saw the loop way, but I promise you, especially once you get to CSCI 41, it's impossible to do something non-recursively, more or less. Okay? I'll show you a good example of that later today too. So let me show you a stack diagram of what's happening here, because that's where the looping's coming from. All right. So the function call stack looks so cool with recursion. So here's what's going on. We're down in main and we're calling fact of 5, and we're jumping up here. We're going to have a bunch of unfinished function calls to fact at the same time. That's going to give us our looping. So main calls, let me draw it like this. Main calls fact of 5. And so, like, I'm drawing it like this just to be lazy, but you got like an n variable, right? It's set to 5. That's your parameter. So that's how that's working. And then fact of 5, well, n is not 1. So it's going to hit the else case, and it's going to return, once it has this final answer, it's going to return its n times fact of n minus 1. So it needs to go off and compute fact of n minus 1 before it can possibly return anything. It doesn't know that answer yet. So fact of 5 is going to be waiting on that line, and it goes off and it calls fact of 4. Does that make sense? It needs that answer. It can't return until it has it. So fact of 4 has its own n variable. It's set to 4. So I have two calls to fact running right now at the same time with different parameters. They have their own local memory for n, and they're different n's right now. Okay, that's key. And then I think you can imagine what's going to happen there. It's going to return its 4 times the result of factorial of 3, which it doesn't have that yet, so it has to go off and ask for it. What's factorial of 3? I'll call myself. Fact of 3. And then fact of 3 is going to call, it's going to try and return its 3 times fact of 2. Doesn't have that, it has to go and ask for it. Calls fact of 2. These are all functions running. They're all sitting on this line right now. Every one of those functions is sitting on this line waiting for the smaller call to finish so that it can return its answer. All right, fact of 2 is running now. It's in the recursive case. It's going to multiply its 2 by fact of 1. So it goes off and it calls fact of 1 before it can possibly return. So I have 5 calls to facts sitting on the stack right now. They're all waiting on each other. All the ones below, at least. And so they all have their own n variable, right? That's the thing that I want the factorial of right now. This n is 1, this n is 2, this n is 3, 4, and 5. So does that make sense? There's 5 separate fact calls right now. They're all waiting on each other. And now fact of 1 was up here. They finally get the base case. All right. So that can return 1 to whoever was calling it, which is always the person below you on the stack. So it is going to pop itself off the stack, give control back to factorial of 2, and give its answer as 1. It's going to return that back to fact of 2. All right. And this is going to kick off the recursion. Now we've hit the base case. It's going to work its way back up. All right. So fact of 2 was waiting on this line for fact of 1. It just got its answer back. It got 1 back. It can multiply its 2 by that 1 and give back its final answer. 2. That's the factorial of 2. And that's correct. Does that make sense? So now we're back in fact of 3. It was again waiting on this line for fact of 2 to finish. It just got its answer back. Finally, it can multiply its 3 by fact of 2. It can give back 6 to whoever called it, which was fact of 4. See how that's working? Unwinding. Fact of 4 was again waiting on this line for fact of 3 to finish so that it could multiply its 4 by that answer. It finally got an answer back for fact of 4, or fact of 3. That was 6. It can multiply its 4 by that 6. It's n by that 6 result, and it can give back 24. That's what it's going to return to whoever called it. And then fact of 5, finally, the original call to factorial, was waiting so long on fact of 4. Fact of 4 finally has an answer. We got it back, 24. It can multiply its 5 by that 24. All right? And give back the final answer to whoever was asking for it, 120 in main, and that is going to be given to C out and printed. Okay? That's what's going on under the hood. Fact of 5 is calling fact of 4. Fact of 4 is calling fact of 3, all the way down to the base case. And then the stack starts unwinding, returning back. Now we have answers. Let's start giving them back to whoever was asking for them, the one bigger version of the problem. Okay? Are there any questions about that? And kind of, do we see how this is mirroring this diagram that I drew up here from before? Kind of doing the same thing. That's the idea. It's working its way down to a base case, building itself back up. That is recursion. Any questions about this code again, now that you've seen that diagram? Does it make slightly more sense? All right. So this is definitely a harder concept, one to study for sure. Let me try and prove to you why recursion works. Okay? Why is it always going to give you the answer back if these diagrams don't make enough sense to you? All right? So here is why a recursive solution always works. You'll have to wait till CSCI 26 to fully get the real proof, but this is a good enough proof, I think. Let's pretend that we are trying to solve some generic recursive problem. Call it P. So we're trying to solve a problem called P. And when we implement the solution recursively, we give a base case and a recursive case, and here's essentially what they're doing. A base case is shouting out to the world saying, I know how to solve P at some very small input. I know how to solve P of 0. I know how to solve the smallest problem. All right? And the recursive case, what that is doing is it's saying, assuming you give me a solution to a size k problem, I can build for you the answer to a size k plus 1 problem. So you give me a one smaller answer, I can give you the solution to the next bigger problem. All right? With variables that looks like this. You give me P of k, I can transform that into a one bigger solution. That's exactly what this factorial is doing. You give me factorial of n minus 1, I can transform that into the factorial of n for you. All right? So these are the two pieces of a recursive solution, deep down, mathematically. And if you think about them long enough, you can use these two rules together to solve any P of n for any n that's greater than or equal to 0. I can give you the answer to any for any input, as long as it's greater than or equal to 0, because I can use these two rules in tandem. All right? Watch. So here we go. It'd be like P of 0. I have that immediately. I can just say it. It's there. I have it. And then I can start running this rule forever. Set k to 0. That gives me a way to go from P of 0 to P of 1. See that? And now I have P of 1 at my fingertips. I have that answer now. Now I can run this rule with k equal to 1. It's saying if you give me P of 1, I will give you P of 2. I'll give you that one bigger solution. Cool. Here you go. P of 2. And then if you give me P, now that you have P of 2, you can run this rule to get the answer for P of 3. You see that? That's essentially what's going on. That's what recursion is doing. We think about it, and you can build up any number, any answer. When we implement this, though, it does start from the top, and it works its way down to the base case, as we saw. It works its way down this way, this way, this way, and then it starts going in this order. That's what we saw with the diagrams. All right? That's the goal. That's why it works, more or less. That's why it'll give you the answer for any input, as long as it's going to hit the base case eventually. There is one secret that I want to at least plant the seed in your mind right now. It's going to make 0 sense, but when you write a recursive solution, there's some magic involved. There's some cool math involved. It's all this stuff deep down. But what you do is you can just assume. You can assume that when you make that smaller call, that's called a recursive call, by the way, that smaller call. Let me underline that because that's an important word that I'll use a lot. This is called a recursive call. So right here, this smaller call, it's called the recursive call. All right? You get to actually just assume that worked when you're writing an answer that's recursive. You can just go and assume, if you're making a smaller call, assume you got the right answer back, right? And it will be correct. You will have gotten the right answer back as long as you build up the larger answer correctly and give the correct base case, all right? Because it will hit that base case and start building itself up with your recursive rule, right? You will eventually get that right answer. The recursive call will have worked, all right? I want you to think like that if you can. It's magical. So really, we didn't even have to do anything. We just needed to notice, in this case, what is the factorial of n? It's n times n minus 1 factorial. I do not have to think anything more after that. I can just call a fact of n minus 1, that's a smaller input. I can just assume that's going to give me back n minus 1 factorial. No questions asked. As long as you give back the full answer correctly and give a good base case, this really will have given you back n minus 1 factorial. But the thought can stop there. That's the magic of recursion. And that will not make a whole lot of sense until you try more examples. But that's the secret. Recursive answers, you can stop thinking about what's going to be called after that. Just you make that smaller call, just assume you got the right answer back. And this is kind of why you can assume that. All right? So I think that's all that I wanted to say there, which probably has thoroughly confused you. I'm sorry. But that is somewhat helpful. I want you to have heard these words once before you hear them again. Any questions about any of that? Because now I have more examples that'll make more sense. So here's another example for you. I claim that computing a number to an integer power is a recursive problem. So let's say I'm taking 2.5 to the fifth power. 2.5 to the fifth power. That's equal to 2.5 times 2.5 times 2.5 times 2.5 times 2.5, right? We can do this together as a group. Where can you find a smaller power computation in here? Yeah?
2.5 to the power of 5 is just 2.5 to the power of 4 times 2.5.
Yeah, so you can circle it in any number of ways, but do we see how, like, here's 2.5 to the fourth? Or even here's 2.5 to the fourth. Either side. And here's 2.5 cubed. There's a million things. You can break it down in any way. Does everybody see that? It's like, what is this but 2.5 to the fourth power? All right. So we found a power computation inside of a power computation. That means it's recursive. All right. And you can even find smaller ones, like here's 2.5 cubed. You can circle any of them, right? I'm just trying to shuffle them to the right, I guess. But could be anything. 2.5 cubed, 2.5 squared, 2.5 to the first. And if you think about it long enough, you even have 2.5 to the 0th power secretly there. That's times 1. That does nothing. So, interesting. All right? Let's make that. We'll call it POW. So, POW, x comma y, takes two things. That's going to compute in that order. Let's say that it computes x to the power of y. All right? So, we found that smaller power computation inside of the bigger one. So, like 2, let's just say just 2 to the 4th power. 2 to the 4th power, that's equal to 2 times 2 times 2 times 2. What is that but 2 cubed? So that's equal to, what is 2 cubed equal to but 2 times 2 times 2? And I see a 2 squared there. So do you see the recursive case? Can we generalize this? Recursive case. You ask me for any number, call it m, let's say, to the power of any other number, as long as n is an integer, call it n, that's equal to 2 to the 4th is equal to 2 times 2 cubed, so m to the n is equal to m times m to the n minus 1 power. There's your smaller power computation. Does that make sense? That's going to be your recursive case. That's your recursive case rule. And then we have to go and find a good base case. So let's keep running this rule. 2 squared, that's equal to 2 times 2 to the first. If we run our rule, let me draw that slightly better. 2 squared is equal to 2 times 2 to the first. Running our rule, that still makes sense. 2 to the first, that's equal to 2 times 2 to the 0th power. That still makes sense. And then you can keep going, like 2 to the 0th power, that's equal to 2 times 2 to the negative first power, which is equal to 1/2. And so like that, technically correct, but that doesn't really give us much. This just becomes 1, right? There's no need to keep going. So I think a good stopping place is, like, you asked me for the 0th power of something. Anything to the 0th power is always 1. So I can just it gives back 1. Does that make sense? That sounds like a good base case to me. And if you think about it long enough, you might agree on that too. So that leads us to a base case rule. We always need that. We need to stop our recursion eventually. So you ask me for m to the 0th power, I can immediately tell you that the answer is 1. That's the idea, right? So that's it. The recursive case, its job is to go off and hand the problem off to a smaller power computation, and then once it gets its answer back, it can build up the original answer, the bigger one, and eventually it's working its way towards that base case, which is going to stop everything and start building things up. All right? That's that. Let's program it. Dun, dun, dun. Pow.cpp. So, I don't know. What was our original one? See how power of 2.5 to the 5th power? And we'll do some more. Let's do like 2 to the 4th power. That was my other example, right? And then 2 to the 5th power. I don't know. Sounds good to me. So, alright, let's make a POW function. It takes, the second thing, the power needs to be an integer, but the first thing can be a double. Double m int n. And so it's computing a double then, if you allow for double bases. So this is supposed to return m to the nth power. So just like this. You give me m to the n, you're asking me for m to the nth power. I need to figure out if I'm in the recursive case or the base case, first of all, because I don't know which rule to run yet. And after that, I can do my thing. So if n is 0, that means I'm trying to take something to the 0th power. That's my base case. Base case, anything to the 0th power is 1. So return 1, or 1.0 because we're returning doubles just to make it explicit. Otherwise, we're in the recursive case. Recursive case. M to the nth power is equal to m times m to the n minus 1th power. That's that. And so return. How do we translate this into a value? Well, return my m times m to the n minus 1th power. That's me. That's a smaller call to me. Return m to the n minus 1th power. Just like that. And you get to assume that this call really will give back m to the power of n minus 1. You don't need any extra thought. Just assume that gives you that back. Use it to build up the bigger answer. It will be correct. All right? That's the magic of recursion. I want you to start believing in it slowly but surely. All right? So that's that. And let's go off and compile. And so apparently these are the answers. At least 2 to the 4. 2, 4, 8, 16, yes. 32 is one more. So I assume that this one's correct too. All right? So that is our power computation program. Recursive. Any questions about that? Yeah. What do you mean, like using m and making m smaller?
Like if you had a negative, but then you just incremented it by n plus 1 every time?
Yeah. Using... I think that could work. Yeah, something like that. But I think maybe if you ever saw like 2 to the negative 2, I think the easiest way to like give the answer back would be to like compute the reciprocal of your input, like create 1/2, and then send it to your normal POW function with just squared it. I think that would be an easier option, but I think there's probably a way to make this recursive without doing that. But yeah, I think you might have to like divide as you multiply or something like that. I'm sure there's a way though. Yeah, that's a good thought. Any other questions? Let's see here. Oops, I didn't want that. Let me draw another picture. How is POW 2.5 working? So we call it from main, right? Main called POW of 2.5. Let's make this small enough so that I can draw a lot of stack frames. So main calls POW of 2.5 to compute 2 to the 5th power. Okay, and so then we're going to jump up to here. 5 is not 0. So we're in the else case, recursive case, we're going to return our 2 times 2 to the 4th power. We're going to go and call ourselves. We need that answer first. So pow of 5 is waiting on that last line, ready to multiply its 2 once more by the result of pow2 4. But it needs to go off and compute that first. Right? And likewise, 2 to the 4th power is equal to 2 times 2 cubed. It'll be waiting on this line again, asking for the solution. Pow of 2, 3. And I think you get the idea now. Pow2, 3 is going to call pow2, 2. Pow2, 2 is going to call pow2, 1. It wants to multiply its 2 by it. And then pow2, 1 again hits here once more. It's going to return its 2 times 2 to the 0th power. We'll go off and ask for that. So this is, 6 separate calls to pow sitting on the stack at once. They're all waiting. All the ones below are waiting on the one up top. And all of these are their own function call. They all have m's and n's to themselves. So like this m is 2. I guess the m's always 2. But this n is 0. And this one has its own m, which is also 2. That's the input parameter. And then 1 is the power. Okay, so those have those. And then pow2, 0, notice is like, oh yeah, my n is 2. So, or my n is 0. That's my base case. Return 1. I will return 1 to whoever called me. I did my job. So now we're back in pow2, 1, which was waiting right here on pow2, 0. It got the answer 1 back. It can multiply its 2 by that 1 and give back its final answer. It's ready. It knows what to give back and give back a 2. And which is correctly 2 to the 1st power. This is why you get to assume these things. As long as it's being built up correctly, it's working. And then that was given back to this call here, pow2 squared. It was waiting on pow2 the 1st to multiply its 2. It can now return an answer. Boop, it can return 4. Back to whoever called it, which was pow2, 2, 3, which was waiting on pow2, 2 to multiply its 2 one more time, so it can give back 8. That is the correct answer for 2 cubed. Yeah? And then pow2, 4. We're back in pow2, 4, which is waiting on pow2, 3 to multiply its 2. And then it can return that answer now that it can compute that. So it can give back 16 to whoever called it. And then pow2, 5 was the last original call. It was waiting on pow2, 4. It finally got an answer back. It was being built up slowly but surely. It can multiply its 2 by that and return its answer. Back to main, back to whoever called it. And that's your 32. And then main was sending that to cout. 32 we saw on the output. Does that make sense? Now that's working its way down to the base case. We need to stop eventually. And then building the answer back up using the recursive rule. Now everybody's happy. Alright, let me go with that. So, with great power comes great responsibility. So there's a new kind of error now. You can have an infinite loop recursively, can't you? You can mess something up. So that kind of messing up is called a stack overflow. Now you know what that website's named after. You've been using so much probably. When you have an infinite loop, just like for iterative solutions, you can have an equivalent infinite loop with recursion. That just means you keep calling yourself forever until the end of time. Every call, like you need room for your parameters, every call to a function takes up memory. So you actually cannot have a program last forever if it has an infinite loop recursively, because it will call itself so many times that you run out of memory to make the next call. All right, you can't have that much stuff on the stack. It will run out of memory. That's called a stack overflow. Your stack has gotten so big, you tried to call yourself so many times, 100 times, that you've run out of memory. All right, and that's different from an infinite loop. It won't go on forever. It will stop the program with an error because of that. All right. Because each stack frame, every time you call a function, it takes up memory. It needs to store its parameters, its local variables, like where it's going to return to. That's all there. So, yeah. That is called a stack overflow, and there's some easy ways to get one. All right. If you do recursion wrong, there are some easy ways to get one. The easiest way to have a stack overflow is to not have a base case, because that means it's just going to keep calling itself using the recursive rule until the end of time, and it will never get to a smaller place where it can stop. It'll just keep getting smaller forever. All right, so let me show that to you. Let me steal our factorial program, and I'm going to mess it up in a few different ways. Stack overflow.cpp. Boop. So let's see. Let's call this fact1. So n times fact1 of n minus 1. And let me introduce a problem. Let's be like, I'll delete the iterative version because we don't care about that anymore. And fact1 of 5 or something. I don't know. So here's fact1. I'm going to introduce an issue. I'm going to say issue 1 forgets the base case. That's a very easy way to do recursion wrong. If you forget the base case, you're just always going to return this. It's going to be like, all right, the answer is my n times fact1 of n minus 1. And then it's going to see that input to the next recursive call. It's like, all right, I'm going to multiply my n minus 1 times n minus 2, fact of n minus 2, go off and call that. So it'll just keep calling itself forever. Does that make sense? You see how that's going to happen? So that's a problem. For fun, let's print out as it's calling itself. See out inside fact of what? Let's print our n. And a new line. Just to watch it blow up. It'll be fun. So here we go. It's going to call itself G++ stack overflow. And if you're fast, you can stop it before it stack overflows, maybe. So I'm calling fact of 5. I'm going to have my finger on Control-C. Boop. So cool, I got it before it stack overflowed, but do you see how it kept going smaller and smaller into negative values? It would never have finished. All right. So if I let it run, dun dun dun, dun dun dun. Oh shoot! Did I mess this up? Sorry. I think I did. I think it's optimizing this. Let's see. There's a problem. That wasn't true last time, so they updated. This is cool. Let's see here. This is undefined behavior. It's going to fix it somehow. Gosh.
Just see in the number. So it changes. So it can optimize away what numbers to find, right?
That could potentially be the. I don't think that is the problem though. Let's try compiling it with O0. Oh man, that's so sad. This worked last semester, I promise. Darn.
Or is it just not taking up enough memory to hit the...
I guess that's possible. Did I make my stack space huge? Let's try letting it run for a while. Or let me get rid of the cout so that it can do it faster. Okay, cool. So yeah, apparently it was able to make that many calls, which shouldn't be possible. But I guess, yeah, if you let it run long enough. That's so weird. Now we know. Now I'll remember for next semester. But yeah, apparently the printing made it so slow. Like it was able to call itself a couple 100,000 times. Because I guess you don't need much memory to store one variable. I guess that makes sense to me. But eventually it got so large that it segfaulted because it ran out of memory. It's trying to add a new stack frame right to memory there, and it couldn't write. It got a segfault. So now you know what that means. So I'll keep the cout in. Try to keep it running. You can compile it on your end. See how many times it can get to. Which is kind of funny. Think about that it's not gonna. It's gonna go even farther. Wow. What if I change this to new line? Endl buffers the input, or it flushes it. So let's see if this is any faster. Not really. I'm just going to let it run as I implement another incorrect factorial.
Won't it buffer every time it returns the new function?
It might have made the printing faster. So, okay, apparently it can call itself 261,000-ish times before it segfaults. Now we know. How fun. So, I like that. I guess I could have kept the endl. Just needed to wait longer. I was impatient. It did make it slower, though. So that's one problem. If you forget the base case, it'll go on forever. The next easiest way to have a stack overflow is to make a recursive case and not make progress toward the base case in that recursive case. You have to call something smaller. If you don't do that, you're just like, all right, the factorial of n is the factorial of n. Then it's going to mess up and it'll just keep calling itself again. All right, so let's show that. So that's the other way of messing up. We could even have a correct base case. Whee! So I'll call this, oh, not there, sorry. Wrong program. This one. Fact of 2, I'll call this fact of 2, fact 2. And so it'll call itself. You can have a correct base case, and we'll say we're inside fact, this is fact 1. We'll say we're inside fact of 2, call it on n. And if we're in the base case, that's fine, that's correct. Recursive case, let's make an incorrect one. Let's be like, you're asking for the factorial of n? The answer is the factorial of n. Technically correct, but do you see how this will just keep calling itself? Like, fact of 5 will call, all right, I'm going to return the result of fact of 5, which will return the result of fact of 5, fact of 5, fact of 5 forever until the end of time. All right, so let me comment out this first one so that I can run fact 2. So here is your other issue. So it's going to just call itself a million times. I'm going to call the same fact of 5, or whatever I pass. I'll get rid of this O0, I guess it was unnecessary. After all. And so it's calling fact of 5 a million times. So you cannot assume that this gives you back the right answer, because it won't. You can't assume that that's n factorial, because you didn't make a smaller call. All right? And so again, it's going to call itself a couple 100,000 times and run out of memory. That's the idea. All right? Any questions about that issue? That's another way to get a segfault. Another way, that is a stack overflow. All right? That's all. So remember to make progress towards the base case, otherwise you'll never stop. And then also make sure to have a base case. Also important. All right? So I think the last thing that I want to show you today is a magical thing. It's called the Fibonacci sequence. Have you heard of it before? It's in that one book that Nicolas Cage starred in the movie for, right? Fibonacci sequence. So it's everywhere. It's like, it's in nature. It's so cool. The Fibonacci sequence is this. It's like, it's the spiral. It's everywhere. It's the natural stuff. You can find it in real life. It's some magical thing, and you have a bunch of people talking about it here. Yeah, you can find it in nature. It's so cool. It's everywhere. But here is what it is. It's just a sequence of numbers. It starts with, let's say the first Fibonacci number is 0. Then the next Fibonacci number is, oh, wrong way, sorry. Then the next Fibonacci number in the sequence is 1, then it's 2, then 3, 5, 8, 13, 21, 34, 50, all those ones. And it just goes on forever. And the way that you generate values of the sequence are you start with 0 and 1, and then from then onwards, like the next number, like the 8, is made up of the addition of the 2 previous numbers. So 3 plus 5 make 8. 5 plus 8, that's how you get the 13. Okay? 5 plus 8 is 13, 8 plus 13 is 21, and so on and so forth. That's how you generate the Fibonacci sequence. And apparently, like the Fibonacci sequence approaches, like the ratio of the numbers in the Fibonacci sequence, as those numbers get large, they approach this mathematical constant called phi, which is that thing in nature everywhere. So, yeah, this is the Fibonacci sequence, though, and we would like to make a program that generates it. All right, that if we ask for, like, I want this number in the Fibonacci sequence, tell it to me, we can go off and compute it. And this is a recursive problem. Do you see it? So if this is the sequence, 0, 1, 1, 2, then 3, right, then 5, then 8, then 13, dot, dot, dot. And you're generating them this way, right? 0 plus 1, you add them up. Add these two. That gives you the 1, add these two, add 1 and 1, that gives you the 2, add the 1 and the 2, that gives you the 3, and so on and so forth. That's the idea until the end of time. Let's say that the 0th Fibonacci number is this one. Let's give them indices. This is the first Fibonacci number, index 2 of the Fibonacci sequence, 3, 4, 5, 6, 7. All right? So let's do that. And let's say we want to make a function called fib of n that calculates the nth Fibonacci number. Okay? So notice, do you see the recursive rule? You see kind of how, like, fib of 7, the 7th Fibonacci number, you see where the recursion comes into play? What is fib of 7 but the sum of fib of 5 and fib of 6? Those are smaller values in the sequence. Ooh. Fib of 7 is like fib of 6 plus fib of 5. Do you see how that's recursive? Smaller inputs? Cool. And so that's your recursive case. If you just generalize that. Recursive case. That is, all right, you ask me for fib of n. That's equal to fib of n minus 1 plus fib of n minus 2. Two recursive calls. Cool. Fib of n minus 2. And then you also need two base cases. Two base cases. Let me show you why. You got to start the sequence somewhere. And you definitely have to say that fib of 0 is 0 because there's no two things before that you can sum, right? You have to be like, this is where it starts. I can't go to index -1 and -2 and add them. Those don't exist. So you just got to say fib of 0. That's 0. Define it. But you need another base case for fib of 1 too. You have to say that fib of 1 immediately return 1 as well, because if you were asked to find fib of 1 using the recursive case, it would try to add fib of 0, which exists, to fib of -1, which does not exist. So you can't run that recursive rule again. So you need two base cases. You got to start it off with two values. Okay? And then from then onwards, you can use the recursive case. That's the idea. So you need two base cases and two recursive calls in the recursive case. Remember that a recursive call is just you're calling yourself on a smaller input. Okay. Let us implement this, and there is a bit of a problem, but we'll get there. Dun, dun, dun. Dun, dun, dun. So I will say cout fib of 7. Give me the 7th Fibonacci number. We're going to make a function that does that. So called fib takes an n and gives you back an int because Fibonacci sequence numbers are ints. And so this will return the nth Fibonacci number. All right? And so let's implement these rules. Recursive rule, recursive case-based cases. I should make that plural. It would bother me if I didn't. Sorry. Not one base case, but two. Two of them. Boop. There. All right. So we got to figure out, are we in a base case or are we in the recursive case? That's always your first step. Which rule do I run? You got to figure it out with an if statement. So let's check. Are we in a base case? If n is 0. If that's true, that's one of the base cases. We return 0. Else if n is 1, that means we're in the other base case. We got to return 1. See that? Otherwise, else, then we're finally in the recursive case. My answer is the nth Fibonacci number is the n minus 1th Fibonacci number plus the n minus 2th Fibonacci number. Okay? That'll be how that works. Fib of n minus 1 plus fib of n minus 2. Make two calls, two recursive calls. That's so cool. And that is a recursive problem. Fib. And what do you know? We get 13 as our answer. Are there any questions about how this code is working? How it corresponds to what we came up with, our rules? Making no sense, but you got two base cases now, and you're calling yourself twice. Which kind of makes the diagram, if I were to draw this, a little weird, because I have to erase things and write new things, because fib of n minus 1 needs to get called first, and then fib of n minus 2 is waiting on that. So you need both of these answers before you can return something. So there's like a waiting game to play there. But also, the recursive implementation for Fibonacci, unfortunately, is horrible. So this code that I just wrote, yes, it works, but if I were to ask for fib of I don't know, 100, which you could compute with a loop normally, it's what's the problem? The issue is that it's making two recursive calls and it's doubling work. So we'll talk about this more next time, but let me try and show you the issue. I was impatient before, I am definitely impatient now. So I called fib of 100, trying to calculate the 100th Fibonacci number. It would be printed here if it was ready for it. It is not ready for it. So we can sit here for a while, but if somehow we were able to give constant power to this laptop for a while, we would be sitting here and we would all die by the time it was ready to print something. Actually, the sun will have exploded by the time it will have printed something. There's something horrible going on here that's very subtle. The amount of time that it would take to compute fib of 100 with this code would take longer than the universe has existed. Okay, try and imagine that. That's crazy. So the issue is this right here. We're doubling work in this recursive call, and it's like it's redoing some stuff. We'll get there next time, but I'm going to press Control-C because we don't have all of our lives for this class. So yeah, interesting little problem there that you do have to watch out for sometimes with recursion. So that's a fun little idea. But it would not run out of memory. Surprisingly, it would keep running. It would eventually finish. If we gave it enough trillions of years, it would finish. But we don't have that much time. So, any questions before I talk about your next lab? That's a fun idea to end on, I think, for the day. Let's see. I'm going to stop this, and then go back to here, and then go to here and release lab 7. So this will be due after the midterm. So you can start now. It'll be due in 2 weeks if you wanted that. But definitely after the midterm, lab 7, week 13. Boop. All right, so this one's about pointers. All right, pointers, and we're going to like roll our own version of classes. So I talked about that a little bit. So, okay. There's a few pieces to this lab. Windows desktop started code 40, was it 7? 7? 7. Thank you. All right. Let's see here. Counter test. So here are your files, and the first part is the easy part. I would like you to implement a function called rotate3. What it does is it's essentially swapping 3 things rather than 2 things. It's like it's shuffling them around. It's rotating them. All right. So here's the idea. Like I am passing along the addresses of things. Rotate 3.h. Here's the declaration of this function. You're getting 3 int pointers, and what you're going to do is you're going to rotate them to the right. So you're given a pointer to, like you're passing along, you're calling it like this. You have 3 int variables somewhere, and you pass along pointers to each of them, to this rotate3 function. And your job is, by the end of this function, using those pointers, rotate the values. So the new value of y is the old value of x. The new value of z is the old value of y. See that? And then the z wraps around into the x. So this is like, if this was the initial values of those variables that you were pointing to, these are the new values of the variables that you were pointing to. So it's like swapping, but there's a third thing. That's all. Does that make enough sense? So here's the declaration again. You're getting int pointers, and I want you to rotate these values to the right. So b is going to become, star b becomes the old star a or whatever. Okay? Just use this diagram as your guide. It should help. But that's going to be the declaration. Go and implement it here. And so, like, here's another example. If, like, somebody called it like this, they made these 3 variables and called rotate3 with x, y, and z, then y should become 42, z should become 43, and x should become 44 if these were their initial values, right? The final thing is, in my tests, I'm going to be a little tricky. So if any of those pointers are null, your function should do nothing at all because you don't have enough values. So you should check for null for each of them first. Okay, that's the final piece of that function. Any questions about it? And here's its declaration again. All right, so that's rotate3. Just follow the diagram and the comments. Should be fine. And then, I think this is the other. There's only 2 parts. This is your other part. I'd like you to make a fake class. And let me tell you what I mean by fake. So there's counter.h. We're going to make a counter class like I've explained. You can make your own classes secretly if you wanted to. This is like how the Linux kernel works if you care. You can make a struct, because you can have objects still, just no methods. All right? We're going to make our own counter class without using classes. All right? So secretly, do you remember when I said this? When a member function gets called in C++, secretly a pointer to the object is getting passed to you. It's called your this variable. Maybe you've been reading about that too. So instead of this, we're going to use, we can't reuse that name in C++ because it's a keyword. So we'll use self. We'll use the word self, which is actually what Python uses for this concept, so that's fine. So the compiler does not complain. So each of our methods will take a secret first parameter, which is a pointer to our counter object. So we're trying to build up a counter class. Okay? Here's our goal. So every time we call a function, which is supposed to function as a method, like counter inc, we're going to make a function that increments a counter, and we're going to pass along a pointer to the object we want to mess with, because that's secretly what C++ is doing for you when you really use classes, right? So I want you to understand that by doing this part of the lab. So if, for example, you're implementing counter inc, so here's like an example method. You're given a pointer to a counter called self, and you're meant to increment that counter. If you don't want to think about classes, just think about it that way. It's a function, you're given a pointer to a counter, it's your job to increment that counter. So mess with its count. So this is what the memory looks like. Your job is to set the count inside that self is pointing to, counter object, its count, set it to 43 from 42. Right? So take it whatever it was and do plus plus on it. All right? So you're going to have to figure out how to traverse this pointer to get to this object and then get to the count member variable. Right? It's a two-step process. Because self is just a number. It's just a big number. That's your address. Right? So you got to dereference to get to the counter, and then like use a dot or maybe the arrow to do both to get to that count member variable. That's what lives inside of a counter. All right? Does that make enough sense? You're going to be passed along objects like this. And so maybe look at the tests for extra help, but this is what you're being given. Right? So a constructor for a counter, secretly, you give it the address of the counter you want to construct, you're trying to do stuff to, and then you can give it a starting value. This is a default parameter, by the way. Did we read about this in our textbook? A default parameter? You could have an equal sign here, and it will, if you omit this parameter, it will just pass along 0 for you into this value, into this variable. You can only put the equal sign one place, though, so you can't just copy and paste this and give this a body in the CPP file. You have to get rid of the equal sign 0, right? So just read the comment, and that'll make sense. But that's called a default parameter. So here is the CPP file. You're just going to implement all the functions in the CPP file. All right. I didn't give you anything extra that's helpful there. Let's see what else. So constructor should set the count inside of this counter that is pointing to whatever starting value is. Inc should increment it. Reset should take a counter, like go inside of this counter and reset the count to another value, because that's all a counter has inside of it. It's just a count. And then you have a getter. Here's your getter. Counters get count method secretly. It's a const method, right? So let's pass along a const pointer to our object so that we can only go inside of it and get the value back to return our count. Okay? So do those 4 functions that are pretending to be methods make enough sense? This is secretly what's going on in C++ when you make method calls. It's passing along. Secretly, all of your methods are functions. And secretly, there's always a 0th argument that is a pointer to yourself, which C++ calls this. We cannot reuse that, just like we can't make a variable called double or something. So we're calling it self. Okay? That's the idea there. And I made you some tests. Counter test. Oh, no, I didn't want to change it. And so here are a bunch of them. Testing constructors, inc, and reset. Get all those to pass, please. So like here's a constructor test. It makes a counter object. It calls the constructor on it. So it passes along the address of that counter, sets it to 42, and hopefully the count inside that counter should have become 42, right? Passing it along. Here's a test for inc. So here, I'll make a counter on the heap. Why not? And we'll construct it and inc it 3 times. And so this is essentially like, if I was using classes and I said c.inc, it's really getting translated into something like this. Something like that. Really, I should have been like C arrow inc, whatever. You get the idea. So the count inside should be 3 now. All right, so that's that one. Test reset, test get count. Like if I set the pointer, or if I set the count to 42 and increment it, then the count should be 43 at the end. So those are some simple tests, I guess, right? Get those passing, and then your job is to write 2 more. So I want to see 6 passes in the output. All right, that's the goal for you. All right, so once I get my test passing, write 2 more. Come up with some scenario of like, all right, I'm going to ink it a bunch of times. I'm going to reset it. I'm going to ink it some more. Then I'm going to get the count twice. I don't know, make sure it didn't change. So come up with some weird scenario and make a test for it. Run the code in your mind and check that what you got was what you expected to get, what you expected to see, right? So that is your counter part of this lab, those 3 files. We good with that one? So rotate and counter are your 2 pieces, and you are going to be submitting 3 files. So the rotate implementation, the counter implementation, and your 2 tests. Right, so 3 files total, and there's all that fun stuff at the bottom there. So I think that is all that I wanted to say. That is your lab 7. I'm asking you to use pointers. Any last questions about anything? I think that's all that I wanted to say here. Yeah. Don't forget about your midterm, and the rest of the time is all yours.